Hello, I'm Abhishek Shetty from UC Berkeley. Today I'm going to talk about the connection between matrix discrepancy and quantum communication complexity. This is based on joint work with Sam Hopkins and Prasad Raghavendra. The probabilistic method is a ubiquitous technique in combinatorics and computer science. It's based on the idea that random objects satisfy surprisingly good properties. It is used to construct a variety of objects such as Ramsey graphs and expanders. The two main workhorses in this technique are the Chernoff bound, which controls the tails of sum of independent random variables, and the union bound, which bounds the probability of the union of events. An important application of randomization is to produce balance. One example of this is randomized control trials. But even in simple cases, we can do better than random. For example, in a one-dimensional case, a simple alternating strategy does better than random assignment. The idea of balancing geometric and combinatorial objects is studied under the area of discrepancy theory. A representative question here is as follows. You are given a collection of M sets S1 to Sm in a universe of size n. The aim is to find the coloring of the elements in the universe such that the difference between the two colors maximized over all sets is as small as possible. Applying the Chernoff and union bounds shows that random signs achieve a discrepancy of square root of n log m. In a celebrated result, Spencer showed that there are signs giving discrepancy of square root n log m over n. In particular, when m equals n, we get a square root n bound. We state this in slightly different notation that helps set up the generalizations that we study. Consider vectors Vj whose ith coordinate represents whether the element j lies in Si. Now, the discrepancy discussed in the previous slide corresponds to maximizing the infinity norm of the signed sum of vectors Vj. Spencer's theorem now states that for any vector bounded in infinity norm, there is a signing such that the signed sum is bounded in infinity norm by order of square root n log m over n. There has been a recent elegant set of algorithms making these signings constructed. The main question at the core of our work is whether this has a non-commutative analog. Before discussing the discrepancy, we first look at the Chernoff bound. There is an extremely powerful non-commutative generalization of the Chernoff bound known as the matrix Chernoff bound. This bounds the probability of deviations of the operator norm of a sum of independent matrices. These bounds and related bounds have been instrumental in TCS, physics, machine learning, and many areas. The main challenge in proving these bounds is the non-commutativity. The main question we ask is whether we can beat the matrix Chernoff and union bounds. This can be formalized as the matrix Spencer conjecture, which states that for any set of n m cross m matrices with operator norm bounded by 1, there is a signing such that the signed sum is bounded in spectral norm by order of square root n log m over n. The matrix Chernoff and union bound give order of square root n log m. This conjecture was proposed by Zuzius and Meka. Progress on this conjecture has potential to lead to interesting techniques bringing together matrix analysis and discrepancy theory. We now look at some evidence for the conjecture. When the matrices A1 to An commute, this reduces to the vector case. When the matrices A1 to An are highly non-commutative, we can resolve this using techniques from random matrix theory. We now discuss some progress on the conjecture. For rank 1 matrices, random signs work. For block diagonal matrices, work by Levy, Rothwas, and Ramdas, and Tadeusz, Chiang, and Rees resolved some versions of these conjectures. There are also some work on related questions by Le, King, and Song. Now we'll discuss our results. We establish a new perspective on discrepancy. We show that there's an interesting connection between discrepancy and communication complexity. Under this connection, vector discrepancy corresponds to classical communication complexity, and matrix discrepancy corresponds to quantum communication complexity. Using this connection, we resolve the matrix Spencer conjecture for matrices up to rank of square root n. This theorem just is the same bound as the matrix-Spencer conjecture, with the additional constraint of the matrices being rank of square root n. In independent and concurrent work, DJR propose a framework towards matrix-Spencer, but under the framework, they only get a constant in the important case when m equals n. In the rest of the talk, we'll first discuss the connection between discrepancy and communication. Then we will discuss the connection between matrix discrepancy and quantum communication. Next, we'll talk about the novel connection between partial colorings and communication. We'll end with a proof sketch of the moderate rank matrix-Spencer theorem. First, let us briefly look at the model of communication. We will focus on the one-way communication complexity of the index function. Here, Alice has an n-bit string x and Bob has an index I. The aim is for Bob to output xi after receiving a message from Alice m. The size of the protocol is the number of bits or qubits in message m. We will focus on private coin protocols. Let us look at a simple version of the connection between communication and discrepancy. Let us say there are vectors v1 to vn and plus minus 1 to the m such that for every xi, the norm of the signed sum is greater than some number delta. This should be thought of as a candidate counterexample to a discrepancy bound of delta. We will show that this gives us a log m plus 1 bit protocol for the index function. Here is the protocol. Let x be the input of Alice. Since the infinity norm of the signed sum of vi with x is greater than delta, there is an index j such that the absolute value of the signed sum along the corresponding coordinate is larger than delta. Alice sends across j and the sign of this sum. Bob, on input I, outputs the jth coordinate of vi multiplied by the sign. We claim that this protocol, on average over the inputs of Bob, has an expected probability of half plus delta over 2n of succeeding. Next, we show a quick proof. Expanding the expected value, we see that this expression is exactly half plus the signed sum along the jth coordinate divided by n, which we assume to be greater than delta. We can show that this correspondence goes the other way as well. Thus, we have a log m bit protocol with expected probability of success half plus delta over 2n is in correspondence with vectors v1 to vn such that the discrepancy is larger than delta. Thus, communication lower bounds are discrepancy upper bounds. We now move to the matrix case. Before that, let us look at some notation for quantum. A quantum state is a PST matrix row of size m cross m with trace 1. A measurement corresponds to PST matrices A1 to AN such that they sum to the identity. This is interpreted as saying state row on this measurement gives I with probability trace of AI times row. The number of bits communicated when sending across the row is bounded by log m. Now consider matrices A1 to AN with operator norm bounded by 1, such that for every sign vector x, the norm of the sum of xi ai is greater than delta. From duality, we have that for every x, there is a PST matrix with trace 1 such that the trace of the sum of xi yx ai is greater than delta. Now consider the matrices ai plus minus as the identity over 2 plus minus AI over 2. These matrices are PSD and each pair sums to the identity. We will use Yx and AI plus minus to construct a quantum protocol similar to our classical protocol. The quantum protocol is the following. Given x, Alice finds Yx such that the trace of the signed sum multiplied by Yx is large. Alice then sends across Yx to Bob. Bob on input I measures Yx with respect to AI plus minus. We can show with essentially the same proof as the classical case that the expected probability of success is half plus delta over 2n. Recall that the statement of Spencer's theorem stated that for vectors v1 to vn, we have that there are signs xi such that the norm of the signed sum xi vi is less than a constant times square root n. Using the connection between discrepancy and communication, this shows that there is no log n bit protocol for the index function with average probability of success half plus a constant over square root n. Now, in the matrix world, the conjecture bound, which says that for all matrices AI with bounded spectral norm, there are signs xi such that the signed sum of xi AI is bounded in spectral norm by a constant times square root n. Using the connection between communication and discrepancy, this tells us that there is no log n qubit protocol for the index function with expected error half plus a constant over square root n. This is all great, but there are some issues. It turns out that it's not clear how to show this average case lower bounds. In fact, even in the classical case, the only way we know how to show these is by essentially proving Spencer's theorem. One of the main difficulties is that the error is extremely close to a half. We'll come up with a connection that's easier to work with by relaxing the notion of a coloring. We recall the notion of a partial coloring. A partial coloring is a vector in the interval -1, 1 to the n with a linear number of coordinates that are integral, i.e. plus minus 1. This notion is standard for proving discrepancy bound. The idea is to first find a partial coloring, then iterate on a smaller instance by fixing the integral coordinates. Using this, we can show how to trade off average case Bob for average case Alice if we replace full colorings with partial colorings. We show the following lemma, which we call the compress or color lemma. It states that for any matrices A1 to An with operator norm less than 1, such that there are no partial colorings, with the norm of the weighted sum being less than order of square root n, there is a log n plus 1 qubit protocol for the index function such that averaged over Alice's inputs x, for every input to Bob, the probability of success is at least half plus a constant over square root n. Thus, to get good partial colorings, it suffices to rule out average case Alice, worst case Bob protocols in the small error regime. Furthermore, the lemma is algorithmic in the sense that these partial colorings can be found using a random semi-definite program. This leads us to the following conjecture in quantum communication complexity. There is a constant C such that for any quantum protocol for the index function on n bits, such that an expectation over Alice's inputs x for all inputs I for Bob, the probability of success is greater than half plus constant C over root n, needs to communicate at least log n qubits. This conjecture, with a few bells and whistles, implies the matrix-Spencer conjecture. We can prove a classical version of this conjecture, which leads to a new proof of Spencer's theorem. In fact, we can prove a quantum version for pure states. This is the key in our resolution of the matrix-Spencer conjecture for moderate rank matrices. Before looking at the proof of the conjecture for classical and quantum pure state cases, we shall briefly look at what is known about the communication complexity of the index function. One can show that for randomized communication, we need a linear number of bits to get a success probability that is a constant above a half. Similarly, for quantum, it can be shown that we still need a linear number of qubits. This result is usually discussed in the quantum literature in terms of quantum random access codes. These proofs all usually involve information theory and Hollow bounds. Unfortunately, for the regime for discrepancy, these techniques do not help. This is roughly because around a half, the binary entropy function behaves like a quadratic. Since we want advantage of about 1 over square root n, this gives us a trivial lower bound. Now we look at the classical lower bound, the regime of our interest. We show that any classical protocol for the index function such that averaged over Alice and worst case for Bob, the probability of success is half plus a constant over square root n. We need to communicate at least log n bits. Given that we have a lower bound in the constant advantage regime, the natural idea is to boost this by repeating the protocol. With advantage epsilon, we need epsilon square repetitions, which implies we have a 1 over epsilon square log n bit protocol. This does not give us a lower bound because we are interested in the regime of epsilon being approximately 1 over square root n. The main observation is that in the repetition protocol, Bob receives messages from Alice and then takes a majority vote. Since majority is a symmetric function, the order of messages does not matter. Thus, it suffices to send the histogram of the messages. The number of possibilities is 2 raised to log n, choose epsilon squared. Here log n represents the length of the original protocol. Thus, Alice needs to send only order of n bits, which leads to a contradiction. This allows us to prove the required lower bound. Moving to the quantum case, we showed there is a constant c such that for any protocol for the index function, such that in expectation over Alice's inputs and for all Bob's inputs, the probability of success at least is half plus that constant c over square root n needs to communicate at least log n pure state qubits. The idea is similar to the classical case. The symmetry observation still holds. In this case, we use the symmetric subspace. The pure state lower bound does not suffice for the matrix Spencer conjecture, but it does suffice for the moderate rank case. We now briefly sketch our proof for the moderate rank Spencer conjecture. The key aspect is the notion of quantum state purification, which states that for any mixed state, we can write it as a marginal of a pure state in n square dimensions. We then use a result of Barvinok and Pataki that states for any compact STP with n constraints, there is a solution with rank square root n. This reduces the dimension from n squared to n to the 1.5, but this is still too large. In order to reduce the dimension further, we sketch the state from n to the 1.5 to n dimensions. The sketching error depends on the Frobenius norms of AI. This is why we have the restriction in our theorem. In conclusion, in our work, we show the connection between quantum information and non-commutative discrepancy. Other examples of such connections are seen, for example, in the Cadison-Singer problem. A conjecture on the index function would lead to a better understanding of the communication complexity of index, which would lead to other applications. Another interesting question is whether there are other applications to problems in discrepancy. For more details, please read our paper. Thank you for your attention.